Yeah, orange is hot. I was actually just listening to a song of this called It's not funny at all, actually. It's about it like fighting out the other cancer. I mean, it's a little bit funny, but it's more like, ugh, this sucks.
If you ask a question in class, you need to make sure that you make it on time. You roasted you, didn't you? Yesterday?
Yeah, it was really rude. Like, would you rather me show up to class prepared and late, or on time with all the material they needed? I almost left the class because I did not want to be there that day. And then he decided to say that and shame me for asking a question.
Oh, he shamed you real good. It's like, ooh. I think that's a lesson to everybody.
I almost walked out of the class. I almost talked back. I was like, I really need to hold my tongue right now.
Hey, it's a baseball. Football?
Baseball. Giants game.
Castro?
Chance to knock out the Dodgers out of the postseason today.
All right.
So it's a big game. The only game they've lost in the playoffs so far was the day that I didn't wear my jersey. So better wear my jersey.
That's awesome.
All right. So Rigney, remind me again if I forget, but I think we'll do melting points after break.
Nice.
Just to give everybody else a chance to get here between now and then.
And you got yours, right?
For methods, I'll be able to
So you know, yesterday I scraped my base sample off the filter. There's nothing there.
Oh, no.
0% of anything was on that filter. Same with yours and same with yours.
Oh, good.
of the diphenylamine.
Yeah.
So maybe we need to let that go longer. So there are a couple things. The diphenylamine in this exercise into acid base chemistry, which makes sense considering that's the lab. Looks like this. And so when it's in its deprotonated form, this lone pair is delocalized because it's adjacent to all these pi bonds in both directions. And that means that you have resonance structures where you have resonance between both of these benzene rings as well. But the second that you protonate this, all of a sudden that lone pair is no longer a lone pair, it's a sigma bond, right? Which means all of a sudden it can't resonate. So not only do you lose the delocalization of that lone pair when you protonate it, you're going to lose the delocalization of this benzene ring being able to resonate all the way over here as well. So you're breaking up a lot of resonance structures. It's not just one resonance structure that you're losing a lot of resonance structures. So with that in mind, we would not expect this to be a very good base. So it's possible we need to get more to increase the acidity levels or just allow it more time to reach equilibrium. Because even if pKa is something like, if the pKa was 8, that's still pretty hard. That's still a reasonably good base. But if it also is going to have if it's not as favored by equilibrium, so if we have a potential energy surface that looks like this, where there's a small difference in the protonated versus or the deprotonated versus the protonated form, we might have a very big activation energy. And remember, activation energy is tied to the rate constant per reaction. So even if we are getting low enough pH to be below the pKa in order to make it protonated, we still might not have been giving it enough time to be protonated because there might also be a larger activation energy than we're normally used to for acid-base reactions. Normally, acid-base reactions, there's almost no activation energy. They are really, really quick reactions. Basically, give it time to mix up, let it settle back into 2 layers, and your acid-base reaction is at equilibrium. But if there's a larger than normal activation energy, because we're breaking up all this conjugation, it's possible we just need to let it go longer, or we need to make it more acidic to favor the protonated state more in order to get it to be more soluble in the aqueous layer. So, good feedback from you guys that one didn't work, because it should have worked on paper. So something about the procedure itself made it so that one didn't give us good yields. Good question about repercussion for runoff. Ken and I were actually talking about fertilizer runoff earlier from the keys. And lawns in general in Tahoe are not very good for lake clarity, even if they're not in the keys, because if you fertilize your lawn with pretty much anything, natural or not, it's not an organic versus I'm using organic in the marketing sense, not in the chemistry sense. It doesn't matter if it's synthetic or what's considered organic fertilizer, it's still just as bad for lake clarity. Organic fertilizers, which basically cow manure, are typically a little bit better when it comes to runoff, because there's a little bit more of a solid matrix. It's insoluble, that doesn't run off, and tends to retain some of those nutrients a little bit better. But still, for the most part, both of them, any fertilizer is going to be really bad for the lake clarity and clarity of any streams or rivers that are affected by runoff. Which is one of many reasons why they're trying to get people to replace lawns in the Tahoe Basin with native species, native plants. One, is lower maintenance. 2, requires less water. And 3, you don't have to fertilize it. So there's going to be a lot of issues with when it comes to, I don't know specifically, we could probably look up numbers for the Angora fire, and if there was a noticeable difference in lake clarity for the 5 years following the Angora fire versus before. So I don't know 100%. I do know that fire retardant is not very water soluble. So in general, that's going to be less of an issue when it comes to anything else. What's going to be a bigger issue is just going to be the sheer amount of carbon in the form of soot and ash that gets washed in, because that's going to affect lake clarity as well. And the nice thing is carbon's not a super important nutrient when it comes to, it's usually not the limiting factor when it comes to algae growth and microorganism growth. Phosphorus and nitrogen tend to be the limiting factors. So all the carbon, all the soot that is going to get washed into the lake might affect lake quality for a year, but probably not longer than that. And it's probably more just in the sense that it's more like dust. You have to wait for it to settle. Shouldn't affect the microorganisms too much, I wouldn't think, because they're already starved for nitrogen and phosphorus. So adding more carbon is not going to help them grow anymore. But that's all just me speculating as a biochemist. I'm not a hydrologist. Scott Valentine would probably be the one to ask, but I believe his degree is actually in hydrology. So he'd probably be able to give you a more complete answer on that one. And then this was a good question, because we're going to talk about, you guys are going to do distillation lab today. What is about alcohol that can cause your skin to get, so there's 2 different things happening here. When you drink alcohol, you get dehydrated because your body uses water in your urinary system to flush everything out of your body. And so you wind up needing to pee more, and you wind up dehydrating yourself, both because the process of digesting the alcohol requires water, but mainly because your body wants to get all those toxic byproducts out. And it does that by just increasing your urinary volume. When you put alcohol on your skin, like hand sanitizer, something else is happening. So it turns out that anytime, erasers. You can me that, Ryan?
Giants.
There we go.
He's out.
When we start looking at things evaporating, we've talked about phase change in Gen Chem before, but it's a little bit different when you start looking about mixtures evaporating. So normally we would expect if you have ethanol that has a boiling point of say 78 degrees Celsius, and if we have a mixture that's got some water in it, and let's just assume we're at sea level, so for the sake of making easy numbers. We've got a boiling point of ethanol of 78 Celsius and a boiling point of water at 100 Celsius. What we would normally expect to see is if we did sort of remember doing that experiment where we watched ice melt in Gen Chem, your heating curve? Your temperature went up until it got to boiling and then it flattened out, right? And then it kept going. So we might expect to see something that looks somewhat similar. We had a mixture of these two things where once it hits 78, it stays at 78 until all the ethanol's gone, and then it'll go up to 100 and boil until all the water's gone. That's not what we actually see. What we actually see is that as soon as it starts boiling, we actually had a mixture of ethanol and water evaporating off at the same time. It's related to the mole fraction in the original solution. So anytime you have something evaporating in a mixture, it's going to bring a little bit of every volatile component with it when it evaporates. So when the ethanol evaporates off of your skin, when you're using it as a hand sanitizer, it's bringing some of the oils and some of the water from your skin with it as it evaporates. Which means as a result, you wind up dehydrating your skin in that case and drying out your skin. So two very different things happening. One is purely physical and one's more biological in terms of the dehydrating when you drink alcohol. But we can explain drying out your skin entirely due to the physics. Yeah, Hannah?
So you're saying one is going to make sure they evaporate at the same time. Do they evaporate at the same rate?
They do. So what you wind up with, and it's early in the morning and I have not reviewed the equations for this, so I'm going to go off the top of my head and see if I can remember how to do these equations properly. Essentially what you get is, so if you have a mixture that has some mole fraction of ethanol, your vapor pressure of so down here we have our liquid form that's got some amount of ethanol and water. The vapor above it is going to be based on how close you are to the boiling point of each of these separately and the mole fraction that you started with. So the vapor pressure of each of these, so remember, let's see, vapor pressure of anything is equal to the vapor pressure of the pure substance times the mole fraction in the mixture. Right, so if you have more of a mole fraction of ethanol down here, you're going to also have more of a mole fraction of ethanol up here. The problem is you can't just look at that, because what you actually wind up with up here, your vapor pressure of each of these is going to be different than what you started with. So when something evaporates, this is the principle of how distillation works, is that your mole fraction of each compound in the vapor phase is not the same as what you started with. Because the mole fraction that you started with is what goes in here. So this is the mole fraction of the liquid, of the solution. So the mole fraction of the solution times the original vapor pressure of the pure compound gives you the vapor pressure above the solution. And so then your mole fraction of the vapor phase is equal to the vapor pressure of that compound divided by the total vapor pressure, which is barometric pressure if it's boiling. So because you can start with a different mole fraction down here, and at a certain temperature, at a certain boiling point, you're gonna get a different ratio of your two components in the vapor phase. You're gonna wind up with more of one of the compound that's more volatile. Volatile in the chemistry sense just means it evaporates. Whatever is more volatile, whatever evaporates at a lower temperature or boils at a lower temperature, should be present in higher amounts in the vapor phase than the component that is less volatile. So you wind up getting your mole fraction in the vapor phase increases when you distill something. When you then collect the vapor and then you can recondense it, and you wind up getting a more concentrated solution. Right, so that is the basis for how distillation works. Is that by changing, if you know these two numbers, you can figure out what the vapor phase is at that temperature. And if you know the vapor phase of all of the components at that temperature, or if you know that it's boiling and you know what the barometric pressure is, you know this number. So you can actually predict what is the mole fraction in the vapor phase based on the mole fraction of the liquid and the normal vapor pressure at that temperature. Which was a bunch more theory than I was planning on going into right now. I don't think I made any mistakes.
I wouldn't be able to crack you if you did.
At the very least, the concept's right. I may have messed up an equation here or there or mislabeled something.
We forgive you.
It's what happens when I go off the cuff sometimes.
That's the benefit of it, Andy. You can just dish up whatever you want and.
Nobody's in the state to question this.
Sounds good.
And Ryan, this is our solution manual. So anybody who wants to check any of their work on any of the chapter problems, it has all of the solutions for the stuff in the middle of the chapter and the stuff at the end of the chapter. It'll just be in my office. You can come by, take pictures of it, check it out. For the most part, I'm going to ask that you not take it home unless you really need to for some reason, just so we know that it's always here, just like the lending copy of the library, or the reading copy of the library. But it's here if you need it.
Thank you.
You're very welcome. Thanks for reminding me. All right. This was a tricky one. Roughly half of you wound up with the right response. In this case, in both of these compounds, you already have a lone pair that can participate in resonance on this nitrogen, right? So it's actually not the number of resonance structures that's going to affect the acidity. I know that's the first thing I told you to look for. But in this case, this nitrogen's lone pair already, while it's still protonated, is already participating in resonance. So the resonance structures themselves wind up being a more significant piece. Because if you look at the deprotonated forms here, there we go. Versus they both look pretty similar, and this resonance structure for each of them should be relatively the same. The amount of stability. But when you move this negative charge over, and for the sake of making this simple, I'll redraw this the same way. We wind up with a resonance structure that puts a negative charge on the nitrogen, and everything else is the same. versus a carbon, so first resonance structure, all we did the exact same thing in both of these, except this one puts a negative charge on a nitrogen, and this resonance structure puts a negative charge on a carbon. Now, one of our, I think it was the last thing that we looked at was when it came to stability of resonance structures was, well, are we putting a negative formal charge on something that's more electronegative or less electronegative? Carbon's less electronegative than nitrogen, so this resonance structure is a little bit more stable than that resonance structure. And if you keep drawing resonance structures, there's no way, remember how the resonance structures basically make the charge alternate atoms, right? You skip over an atom, which is the net result. We went from negative charge here to 2 atoms away as a result of moving the electrons 1 atom at a time. There's no way you can put the negative charge in this position. There's no way to do that based on where the negative charge starts. You can't resonate it to this position, which is what's called the meta position. Meta means 1 atom removed. So you can't put the negative charge in the meta position, which means no matter what you do, you're not going to get that extra little bit of stability from putting a negative charge on a nitrogen versus a carbon. So that makes this resonance structure a little bit more stable than any of the other possibilities, which would mean the nitrogen that's in this is what's called the ortho position. The ortho position is directly next to the other one. We'll go over all that nomenclature when we get to organic stuff in a little bit anyway. But the nitrogen that's directly next to the substituent is going to be more stable than having it in the meta position. So that makes this more acidic. Barely. If you look up their pKa's, they might be within sig figs, they might be the same. But from a theory standpoint, we can say, well, here's why this one should be a little bit more stable, even if it's not within our ability to measure in a normal lab. And I would wager it's probably more like 1/10 of a pH unit. It should be measurable, even if it's small compared to a lot of the others. Did you look up numbers, Ricky?
Yeah, it was like 0.8.
0.8.
One was like 6.05, one was like 3.85.
Yeah, okay, so that's a little bit larger difference than I would even expect.
So what would you say the first criteria was before you started?
The number of resonance structures.
Thank you.
That's the main thing. Do we get something where we can have extra resonance structures as a result of losing a hydrogen? We don't have that, but what we do get is a resonance structure that puts a negative on a more electronegative element. So the number of resonance structures is not any different, but the stability of one of the resonance structures is greater when it's in the ortho position. Excuse me. All right, any other questions on this one? Again, the biggest thing with acidity that you're looking for is, am I making a conjugate base that's going to have extra resonance? That's going to be the #1 criteria. If you're going to get extra resonance structures as a result of deprotonating something, that's going to make it easier to pull that hydrogen off. And just because my brain always likes to put these things in graphical descriptions rather than just having written descriptions, if we had a potential energy surface, hazards of writing while you're trying to talk means sometimes I write the wrong letters. If we have a normal acid-base reaction that looks like this, by making more stable resonance structures on the products, you're going to lower this energy. Even if you're starting from approximately the same relative height here. And that means one, it's going to be more favored at equilibrium, and two, it's going to get there faster. We can actually approximate where the activation energy should be if we treat these as parabola. Then the linear combination of the two parabola for the products and the reactants where they meet is going to be where you see your activation energy. And so if you lower one of those parabolas, you're by definition going to lower the activation energy.
So there's a basis for this sort of thing?
Yeah.
So that's cool.
It's all mathematical. It's just mathematical, not in 2 dimensions. Because every atom has 3 dimensions it can move in, right? So we don't wind up with a 2-dimensional surface describing this. This might look at, we could actually put an x-axis here, where x was the distance between atom A and your hydrogen. And as the radius gets bigger, that corresponds to the hydrogen being disassociated. Right? Basically, there's some hydrogen bond length, and as you increase that distance, there's going to be a point where you get to an activation energy, and then it starts going downhill in energy. The problem is that every single bond has a dimension that looks like that. So you're dealing with what's called a many-dimensional surface. That's going to be based on the number of electrons you have -2, 3n minus 2. So if you have 18 electrons, 18 times 3 is, I should have picked easier numbers. What is it, 40? No, that's 24 times 3. But regardless, you get a big number, and then you're dealing with something that's not 2 dimensions. It's actually a function that's in this 72 different dimensions. So it's a very, very complex function. But yeah, we can absolutely plot this. We just usually pick one dimension to blow up and consider the most. Like this is the bond that's breaking, so we're going to put that as the x value for this. But yeah, mathematically, it's all there. It's just hard to wrap your head around sometimes. Especially the linear algebra part. All right. So was this question was, which of these is not a valid resonance structure, right?
Right.
Anybody look at it without consulting your notes?
Yeah, my thought process was, C doesn't even make sense to me. How could there be a positive charge with a double bond right next to it? It
Yeah,
doesn't even make sense.
it doesn't make sense, does it?
Yeah.
All the other double bonds are still alternating, so it followed one of our rules for resonance structures, but it put a charge in some more place it's not supposed to be. So yeah, C does not make sense. To be honest, when I first looked at this, I didn't even consider that. I looked at this and said, well, you can't put the positive charge in the meta position. Like we were just talking about. There's no way that you can have the charge jump and alternate carbons and wind up with it in either of these 2 positions. This is the only way they can actually draw that without drawing a carbon with 5 bonds though, right? If you actually made this look better by not having a pi bond to it, you'd wind up having to draw a pi bond, either missing a pi bond completely or drawing it to a carbon that already had 4 bonds. Yeah, all you have to do is look at it and say, okay, if I'm alternating, these electrons are moving over, my positive charge goes there, and then there, and then there. It can't go here to these 2, and it can't go to that carbon. Well, I think as you get more practice with this, you'll start to notice like, oh, that one just looks wrong. I can't put my finger on it yet. But on a multiple choice test, especially if there's time pressure, sometimes that'll be enough. And if you had time, you would come back to it and say, Was I right with that? Was my intuition right, or did I mess something up? But at the very least, it give you something like, well, I'm pretty sure it's this answer, although I couldn't tell you why yet. It just looks wrong.
That was my reason.
And that's fair enough. You guys are getting good enough at recognizing common patterns at this point. Although you should still be able to explain why when you put some thought into it. All right. So we went over complicated branches or branched branches. Was one of the places we ended up at the end of class the other day. And I did go through and look at everybody's answers, and for the most part, on the quiz, you were able to do this properly. If you got marked as 0, it was because you either didn't put it in the same order as I did, or your numbering was a little different. The biggest thing that I noticed is that several people had trouble with some of these with finding the longest continuous carbon chain. Right, so just make sure it's not about just going left to right. It's not about what's simplest, it's about what's longest. So I think it was a hexane instead of a heptane if you counted from left to right on one of them on the quiz. And remember that those parentheses are just mean that we're going to apply one prefix to another prefix. If we have a branch within a branch, we have a complicated branch. So our longest continuous carbon chain here, this one's drawn in an easy way. 1, 2, 3, 4, 5, 6, 7. So it's a heptane. And that heptane has a branch that also has a branch. So parent molecule heptane. Our longest continuous carbon chain from the branch that starts with this is 1, is 1, 2, is an ethyl group. So within parentheses, we'd say, okay, it's an ethyl, and that ethyl has a methyl on it. So that is a methyl-ethyl group, and also called an isopropyl group. You can use that. I would prefer you do this because this will serve you better when we get beyond things that are bigger than an isopropyl group. This system doesn't change. The isotherms do, and the other common names. And then we just specify outside the parentheses where that methyl-ethyl group is. So carbon 1, 2, 3, 4. It doesn't matter which side we count from. It's carbon 4, right? So 4-methyl-ethyl heptane. So here's an example. So isopropyl is what we've been naming a methyl-ethyl group. An isobutyl group looks like that. It's butyl because there's 4 carbons total. When you're using these naming systems, it's the total number of carbons in the branch, not the longest continuous chain within the branch. Right, so I'm showing you these basically to indicate why we don't want to deal with this. Right, because then you've got N-propyl and N-butyl, means it's a straight chain. Then there's sec-butyl or tert-butyl. Tert-butyl would be it's 4 carbons as your branch, and they're all attached to the same center carbon here. So, and a lot of times it's just abbreviated T-butyl. Isopropyl and T-butyl are the only one of these that are commonly used anymore. Just mostly because we have a better way. We don't need to remember all these specifics when we can use the same systematic approach every time. Hannah?
Does the order in which you write those 2 in the parentheses matter?
It does. Because if you said ethyl-methyl, you'd be saying it's a methyl group that has an ethyl on it. So because we're saying, the parentheses are saying this group applies to that one. And so if you switch the order of these, it would make a difference. The nice thing about all of these is they can all be named very predictably and reliably by using the parentheses system, so you don't need to memorize how all these work. But I do want you to be aware that that system exists, and for some reason there are some people who still use it, mainly for isopropyl and T-butyl. So if we're trying to name molecules, if we have a choice in picking the longest continuous carbon chain, you can pick the longest continuous carbon chain that doesn't have any complicated branches. But if the longest continuous carbon chain, you don't have a choice. If you have to go this way to give us 1, 2, 3, 4, 5, 6, 7, 8, versus 1, 2, 3, 4, 5, 6, 7, we can't pick the heptane route here. We have to pick the octane route because that's our longest continuous carbon chain. So it has to be named with a complicated branch. So our longest continuous carbon chain then looks like that. So it's an octane. And once you get the hang of what these look like, you can just remember that's a methyl ethyl group or an isopropyl group, or you can say it's an ethyl group that has a methyl attached. So it's going to be ethyl with a methyl attached, and it's on carbon 1, 2, 3, 4, 4-methyl ethyl octane. One, 2, 3, 4, 5, 6, 7, 8, or 1, 2, 3, 4, 5, 6, 7, 8, 9. You have to go no name. Fred? It would if you counted that as carbon 1. But if you counted this as carbon 1, you can make that number a little bit smaller, which is favorable.
But someone who was, immersed in this field would get it, right?
You would still be able to draw the right molecule that way. But because it makes it seem like if you counted the wrong way, it makes it seem like there could be more isomers than there actually are. I'll be a little bit more strict on that than on the alphabetization. On the alphabetizing, there's no wrong way to draw it versus, or even count the number of possible isomers. You said 4 methyl ethyl versus 5 methyl ethyl, and those are the same molecule. Yeah, we could get to the right structure from it, but you might think that there were more isomers than there actually are. So it's a bad habit to be in, more so than the alphabetizing. 2, 3, 4, 5, 6, 7, 8, 9. All right, this one's worth going through mainly because this one's going to be tricky when it comes to numbering with those locants. So if we counted 9 carbons, we know it's going to be no name. And we have a complicated branch. That complicated branch is 3 carbons long with a methyl attached to it. So this is going to be a propyl group. that has a methyl attached. I'm just going to erase this for the sake of giving myself room to write. But there are two ways we could attach a methyl to a propyl group. So within the parentheses, we still need to specify where this methyl is attached to the propyl. If it's attached right where the propyl group is attached to the parent compound, this is carbon 1 of the branch. So we'd say one methyl propyl group, which is on carbon 1, 2, 3, 4, 5. So it gets tricky to say it out loud because you basically, if you're trying to just say this verbally, you basically have to explicitly say where the parentheses are to be entirely unambiguous, at least to somebody who's not all that practiced. Once you get used to seeing this, you could say 5, 1-methylpropyl nonane, and somebody who knows what they're listening for would say, oh, there's parentheses in between the 5 and the 1. But at this stage, it almost makes more sense to say 5, open parentheses, 1-methylpropyl, close parentheses, nonane, which is a mouthful.
So normally, Sean, where the 5's at, we never actually have a 1, correct?
Yes, we would never put a 1 there. Because if it was 1-methylpropyl nonane, then really we just have we counted our longest continuous carbon chain wrong in that case, right?
Yeah.
So you couldn't reverse these and get a correct name. But it's a little bit hard to see why until you draw out the structure sometimes.
So we're only going to see that number 1 within the parentheses.
Until we start dealing with things beyond just alkanes. Because you could have a fluoro group on carbon 1 without changing your carbon chain, right?
Okay.
I inhaled a piece of toast this morning, and it's just sitting in the back of my throat. You guys ever get that when you choke on something and then never really get rid of it for the rest of the day?
Just give a good half.
Yeah, I'll do that on a break, I'm sure. All right. As usual, I think it's easier to start from the name and draw the structures. One, because you don't have to deal with me being tricky about which way I'm drawing the longest continuous carbon chain. You can draw the parent molecule whichever way is convenient for you. But same general approach. Start at the back, work your way forward. Get your parent molecule right, and then add all your branches. So heptane. 1, 2, 3, 4, 5, 6, 7. 2-methylheptane. 4-methylethyl. 1, 2, 3, 4. It's an ethyl group that also has a methyl attached. We have decane. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. On carbon 4, 1, 2, 3, 4, we have a propyl group, 1, 2, 3. And on the second carbon of that propyl group, we have a methyl. So 1, 2. Right, so this complicated branch is a 1-methylpropyl group. This version is a 2-methylpropyl group. They still have longest continuous carbon chain is 3 for both of them. It's just, are you putting a methyl on carbon 1 or carbon 2? You could conceivably have an ethyl propyl group, right? An ethyl propyl group would be 2 carbons coming off of carbon 1 here. And that's where the system, the sec-butyl, isobutyl starts breaking down, right? Because now all of a sudden, how do you name that using those sep versus iso versus tert? It doesn't work. As soon as you get more complicated than these. Yeah, because you wind up with things like isoamyl. An isoamyl group is a pentyl group that is iso, but it's different than isopentyl. Isopentyl is one thing, isoamyl is a different version that's still 5 carbons. It's just a mess. This is a pain, and it's complicated to wrap your head around, but once you do, it's the same every time. And it does apply to anything. It's not just for alkanes, right? You can have a chloromethyl group or a hydroxymethyl group where the hydroxy is applying to the methyl or the chloro is applying to the methyl. So it really opens up a lot of different ways to name things in a really predictable way when we start adding more functional groups as well. All right, we talked about halogens. We did this exact slide already, so we skipped through this. It has the answers on here because when I was teaching Zoom last year, it was easy to add a text box and just type the answers in as we were going through these rather than writing it on the board. And I must have hit save when I closed my PowerPoint slides last year. Here's one last wrinkle, and barely a wrinkle at this stage. This is just one more way we have of describing alkanes is, well, what if they're not what we call a straight chain alkane? What if our longest continuous carbon group is actually in a ring structure? It's still a hydrocarbon, it's still all sigma bonds, so it's still an alkane, and it'll still behave for the most part when it comes to reactivity and properties. It'll still behave mostly like any other alkane, but we need another way to name these. So anytime we have a cyclic group of alkanes, a ring structure, we just add the prefix cyclo. Simple enough, right? And that can apply to anything. Anytime you say cyclo, you're just saying that whatever follows that term is in a ring structure. And you indicate how big that ring structure is by using our same prefixes. We're going to see that cyclohexane and cyclopentane are going to be the most common versions of this because we're limited a little bit by bond angles, right? Our bond angles are supposed to be but around 109.5 degrees, right, for these tetrahedral carbons, all these sp3 carbons. And so if you start limiting how close these bond angles are by making it a more, what we call a more strained cyclo group, a more strained ring structure. So you can actually have cyclobutane, skeletal structure for which looks like that. But pretty much by definition, you're limiting your bond angles to 90 degrees, right? And they want to be 109.5 degrees. So you're forcing these electrons to be closer to each other than they want to be. So this is not a very stable molecule. Strained cycloalkanes tend to rearrange themselves somehow pretty quickly, and sometimes in a way that releases a lot of heat. So these tend to be relatively explosive compounds. I went to undergrad in San Diego, which is a big Navy town, and one of my professors used to work on developing new explosives for military applications. And he actually came up with a molecule. They synthesized this molecule in a lab. It looked like that.
It's a bow tie.
It is. They actually named it bow tie-ene. Ene means that it's a carbon-carbon double bond in there. It's an sp2 carbon. Bow tie-ene was really, really unstable. And it was not suitable for military applications because it was too unstable. You really don't want your explosives to detonate every time your Humvee hits a bump, right? So they wound up not using that. It's still just a fun little factoid, and does look like a bow tie. And it's really unstable because these cyclopropane groups are now stuck at 60 degrees. And that carbon in particular wants to be at 120 degrees, because that's an sp2 carbon. So it's very, very unstable. Brad?
Does solid carbon go in the same crystal structure? It has to go in the crystal structure?
Solid carbon goes in one of two states. If it's all sp3 carbons, and you get all of them staying tetrahedral, and you get these cyclohexane groups that wind up attached to each other. Because remember, we have three dimensions to work with, right? So cyclohexane is not actually flat. It kind of has this structure that looks like this. Actually got it. So if you use your imagination, remember the dots are further away behind the board, and the wedges and the bond that I drew as being thicker than normal are coming out towards you. It actually looks like this. This is cyclohexane's normal structure. Well, if you can imagine that each of these carbons is attached to 4 other carbons, the structure actually continues in 3 dimensions indefinitely, and that's what a diamond looks like. Graphene, or coal, anthracite, is a whole bunch of benzene rings that are all fused together. So it's a whole bunch of sp2 carbons that are connected in sheets that look like this. And you have to be careful how you do this, or else you wind up trying to draw a carbon that has 5 bonds. Let's see. There's a way to do this that doesn't, that I think might actually be connected to like this. And then it looks like I'm missing bonds in the middle. One of those things that when I try to do it off the cuff, I'm going to wind up doing it incorrectly somehow. All right, well, there's a way to do that so that all the double bonds are alternating, and I'm just not seeing it right now. But that's what graphene is a bunch of carbon, sp2 carbons in these sheets that are, and all of these being trigonal planar means that this is totally flat. That's why I call it graphene sheet. And so those are 2 different forms for solid carbon that behave very differently. But yes, they do wind up, they are just repeating cycles in both cases. It's just a matter of, are they sp3 and repeating in 3 dimensions, or sp2 and repeating in 2 dimensions? Technically, this is the more stable state, as it would be if I put the 5 bonds in the right spot. And so actually all diamonds are spontaneously transitioning back to being graphene. It's just happening at a time scale that is so slow that since the birth of the universe, if you had it started at the birth of the universe with a diamond that was the size of your thumb, it still would be a diamond. Because the activation energy is high enough that under normal conditions, you won't see that happen.
So you need an immense amount of pressure to make it go to diamond.
Yes, and in theory, you could take a diamond and you can actually burn it like you would coal. It just takes a lot of energy to get that process started, more energy than you would wind up getting out of the process. Hannah?
So I'm just backing up to what you just said before. So you're saying the difference that makes one flat and one more 3-dimensional is that one is sp2 and one is sp3, so the
Correct.
difference is hybridization?
Exactly. Because the different hybridization, sp2 is what allows us to make those pi bonds, right? And those pi bonds are only going to be on carbons that are trigonal planar, if they're sp2. And so you wind up with this repetitive structure of trigonal planar carbons that winds up only repeating in 2 dimensions. So you can get one figure that shows both of them. So graphene winds up in these sheets that look like this, that sort of stack on top of each other. It's why graphite is such a good dry lubricant. If you've ever built a plywood derby car and tried to make it go really fast, you take a little graphite dust and you put it on the nails that the wheels sit on, and that makes it go extra fast. Because you wind up with these different layers have nothing really, they're attracted to each other a little bit, but they slide really, really easily. Versus a diamond, which has these, if you can imagine taking these, let's see. See if it'll let me do this so I can draw on it. You can actually pick out 6 carbons. You ignore that one in the back. That's a cyclohexane group. But it just happens to be that cyclohexane group is attached in all directions to other cyclohexane groups in a way that is this repetitive crystal structure. And as a result, you get a 3-dimensional structure where everything's sp3 and everything is attached to 4 other carbons, which is why diamonds tend to be so strong in all 3 dimensions, right? Unless you happen to cut them just right, in the way they cut these is basically by using a chisel and hitting it at a certain angle. You hit it at just the right angle, you get this top sheet to sort of slide off and leave the bottom sheet where it was. So that's the way you cut a crystal, is you have to cut with the grain in a certain way to get it to basically fracture along that grain in a really predictable way. Yeah.
So we're talking about crystals, well, minerals in geology,
Mhm.
now it makes sense.
Yeah, they do, and a lot of them are, almost all the minerals you're going to see naturally are going to be silicon-based. Silicon and oxygen, they're mostly silicates, although there are some aluminates, which is aluminum with oxygen. That's so like sapphire and ruby are both aluminum oxide with different inclusions that change the color. A really, really high quality sapphire crystal, we actually just call it an aluminum crystal, is actually totally colorless. You only get the color from those, but depending on what other atoms tend to be present as impurities. But yeah, so diamonds are carbon crystals, but then aluminum crystals make sapphires and rubies, and most of the other common gemstones are going to be silicates, silicon and oxygen with different inclusions that are going to change the color. All right, so if we happen to, and I know we're about due for a break, and then we're going to go do melting points in the lab after our break. That's one of them. If we have something attached to our cyclo group, doesn't matter. Our naming system doesn't really change. You still just name it as branch. So you can have an ethyl cyclopentane. Right?
I think I know the answer, but I'm not asking. Why do we not count it from the top down around the base?
So that's a good question. That's when we're trying to determine our longest continuous carbon chain, we never count into or out of a ring, because it would get really hard to keep track of what was what. So it's basically out of convenience. We're never going to count into a ring or out of a ring. Either the ring is your longest continuous carbon chain, or it's a ring attached to your longest continuous carbon chain. But the ring is never part of your longest continuous carbon chain. Okay, good question though. I always forget to emphasize that. So this is a cyclopentane group with an ethyl attached. If your longest continuous carbon chain is not the cyclo group, we just use cyclo as a prefix on a prefix.
Show that.
Absolutely. 1, 2, 3, 4, 5, 6. And actually we can kind of put it wherever we want now. Our longest continuous carbon chain is 6, right? So our parent compound is hexane. It's not cyclohexane though, even though there's a cyclo group involved. it's got a pentyl group attached. And we would just say it's a cyclopentyl group. For whatever reason, my mind does not default to putting a hyphen here. I won't mark you wrong to do that, but cyclo is an easy enough prefix that it doesn't get lost in the others, at least to my eye. If it helps you, you can do that. I'm not typically going to do that though. For whatever reason, out of habit, cyclopentyl as one word does not look as wrong as putting the rest of this all as one word. If you had cyclohexane all as one word, that's where it starts getting ridiculous to me. And I can't put my finger on why. This looks okay, but that doesn't. So if you wanted to, for the sake of consistency, just keep putting hyphens in, do it. And then we just need to specify where that cyclopentyl is. And so we'd say 2. And that, now we can put a larger group close to the edge, because the cyclo group, it can't be extending the number of carbons in our parent molecule, right? So you could have one cyclopentyl hexane. Right, and so it's still a matter of which of them is the longer continuous carbon chain. And then you just name the other one as a branch. So if I erased 2 carbons over here, now our longest continuous carbon chain is the cyclopentane, and we would name this as a complicated branch. It would be 1-methylpropyl. We need a number for it, so if we did name this, so it's 1, 2, 3 carbons, so it's propyl that has a methyl on carbon 1 of the branch. Do we need a number in front of the parentheses here? Why not, Brad?
No, I guess we would. No, we don't. This is right off the.
Well, yeah, where is carbon 1 on this, on a cyclo group, right? Wherever it's convenient to call it carbon 1. So if you only have one thing attached to a cyclo group, that is carbon 1 where it's attached. If you have 2 things attached to it, now we need numbers. But if it's just one thing, it's always going to be attached to carbon 1. Because this carbon is identical to that carbon and that carbon and that carbon and that carbon, right? So wherever we put this 1-methylpropyl group, it's going to be the same molecule. Right?
I almost got this. So the branch that goes off to the right of the number 1 there, where does that fall in the naming system? That's the methyl.
The methyl that's attached to the propyl.
Then what's attached to that pentane? The equivalent, yes. And there's the number 1.
So this is the cyclopentane group.
There's your cyclopentane, and there's the number 1. What do we call that branch?
So
Right there,
this
yeah.
is a bond, right?
Yeah.
And so this whole group, if this is our cyclopentane group,
Oh, I got you.
1, 2, 3, that's our propyl group.
Okay, I got you.
And that's the methyl attached to the propyl.
Thank you.
No problem.
So the bond to the cyclo group, we don't consider an methyl. Correct?
Say that again?
So the bond that's connected to the cyclo structure, whatever that may be, we don't consider that a methyl group.
So we wouldn't consider, a methyl group has to have the carbon on the other side of that bond, right? So we're usually not looking at the bonds, we're looking at the atoms for determining what these branches are. When we draw skeletal structures, it's hard to remember that sometimes. But this bond is actually neither part of the cyclopentyl group, it's leading to the branch. But the branch, I guess technically, if we're being picky about how we define things, the branch doesn't start until you get to the carbon. that's attached to the cyclopentane. So this bond is sort of no man's land.
Oh, I see, so that's not necessarily the branch.
Yeah, carbon 1 is the start of the branch.
So if you didn't have the 1, 2, 3, you just had the one branch to one, so you erase that whole top part, you just have a little one branch that hooks out, does that mean that? So there's two branches there, like there's a purple there.
So this is no longer a propyl, right? Now the longest continuous carbon chain of the branch is 1 carbon, 2 carbons.
I got you.
So this would be this one,
Right,
ethyl cyclopentane.
okay. Repetition.
Again, it's these layers of complexity, right, that start to make it tricky. It's simple enough when it's a straight chain alkane, and there's none of its prefixes and parentheses. We'll get to where this is second nature. If we do have more than one thing attached, then we name all of the branches with prefixes, just like we normally would. And we'll just go a couple more minutes so we don't have to come back to lecture after we take melting points. So let's go through this slide, and then that gets us to a good stopping point for today. And then we'll go do melting points in lab, and we won't have to come back to lecture from that. So let's do these two practice slides. So for this first one, if you really want to give yourself to test your geometry drawing skills, try to draw a regular heptagon freehand. It's really hard. Typically what I just wind up doing is I draw half of an octagon, and then I draw half of a hexagon, and then I connect them together. Gets you close enough. If we wanted to name any of these, let's start with this one. It's a cycloheptane. And we have 3 different things attached to that, right? So we're going to need 3 prefixes. We've got a fluoro group, a chloro group, and a propyl group. So again, I'm not going to be picky on the order for these. Just pick an order that makes sense. So the propyl group, we have to, now if we have more than one thing attached, we do have to pick a number. So we can call whichever one of these we want carbon 1, but we want to keep our numbers as low as possible. So it makes sense to call whatever you have 2 things attached to, call that carbon 1, and call that carbon 3. So it's going to be 3 propyl, 1 fluoro, 1 fluoro, 1 fluoro, 1 fluoro, 3 propyl cycloheptane. No single piece of this was that hard though, right? It just looks complicated and sounds complicated when you say it all at once. But it's like the old saying, how do you eat an elephant? 1 bite at a time, right? Start with your parent molecule, start adding prefixes until you're done.
So you're not concerned with the F, with the C, the P as far as the
No, I guess
alphabet on that?
to be as correct as possible, these 2 should be switched.
Okay.
But again, I'm not going to be picky about that. I actually wrote it wrong on purpose to make the point that I don't care about the alphabetizing on this. Our parent molecule here makes it easier to count carbons when they're in a ring structure, actually, right? Because that's a hexagon. We all can look at that and recognize the hexagon. So it's cyclohexane. that's just gonna have some prefixes. Cyclohexane, their parent molecule. It's got 2 methyls and an ethyl, right? So, dimethyl and ethyl. And then we just need to say where they are. So if we want to count in a way that's going to keep our numbers as low as possible, what should we call carbon 1? Top right. Yeah. If we call this carbon 1, go 1, 2, 4. If we call this carbon 1, we have to count the same way, right? So it'd be 1, 2, 5. Call this carbon 1, 1, 3, 4. So if we count, start here and count this way, it has to, you have to count consistently the same way around it. So it's not like we can call this carbon 1 and then that's 2 and that's 3. It has to go the same direction all the time, right? So pick the way that's the most convenient that keeps the numbers as low as possible. 1, 2 dimethyl, 4 ethyl. All right, my advice with these, especially if you look at something and you know it's got a bunch of branches or a bunch of prefixes, just give yourself a whole line on your notes or on your page. Right? Give yourself plenty of room because it's always easier to read it when it's overly spaced out than when you're trying to cram everything together. We all want to save paper, but this is not the place to do it.
But see, people always, I'm sorry, this is something I used to do. Some people always say, we want to save paper, we want to save paper. I already have it. It's too late.
Exactly. The other thing about that is that paper is the definition of a renewable resource. It has to be done sustainably, but they can make paper really, really renewably and sustainably if it's done properly. So it's not something we have to worry about running out of. So in my mind, it's not the place to worry about conservation per se. There are bigger fish to fry there. All right. If we had isopropyl cyclopentane, I'll throw that term back in there one more time. Isopropyl was what we named as methyl ethyl, right? So start with your parent molecule. Cyclopentane. Take a carbon, draw a methyl ethyl group. On a test situation where people tend to mess up with the cyclos, is they'll either forget to say cyclopentane, they'll just name this as pentane. The other thing that people mess up with is they confuse a cyclohexane for benzene. Pay attention to the double bonds. This is not benzene, right? Benzene requires those alternating double bonds for it to be benzene. So when you're drawing a cyclohexyl group or a benzene, be very deliberate about whether you're putting those double bonds or not. Right? And I get it, especially on a test, high stress situation, you're trying to go fast because there's a little time pressure. Don't lose the easy points by not paying attention to the fast stuff, right? 1,1,3 trichlorocyclohexane. Again, when you're drawing the molecule, make it however it's convenient. 1,1,3 trichloro. There's carbon 1. There's carbon 3.
That one's FABs, right? Which one do you want?
No, so because this has to be carbon 1, because there's 2 of them. If I said 1,3,5 trichloro, 1,3,5 trifluoro cyclohexane would look like this. Now it's ambiguous which one's carbon 1, 2, and 1, 3, and 5, because any one of them could be carbon 1. All right. So it's a nice, convenient place to stop. You have half an hour plus 5 minutes to take a melting point. It shouldn't take that long. If you already finished your lab from last week, you may not have any melting points to do, but if you do have melting points, if you have other things to finish up in lab, now is free lab time to do that. And normally you can also, if you have everything done in your lab except for taking a melting point, just come to office hours the next day or later that week sometime. Because that'll be pretty common, because usually you're going to want to wait and let your sample finish drying before you do a melting point. So, and you'll get pretty good at it. It'll be fast by that point. So give yourself 15 minutes when you know I'm in lab or in my office, and just come do your melting point some point during the week. But for now, take this time, finish it up, and come back to lab to learn about distillation later today.